Hello, hello. We're here today talking about LOL charts. So remember with our LOL charts, we call them LOL charts because they kind of look like LOL. Their more formal name is energy bar charts because we're really just drawing a bar chart about the thermal and phase energy changes for a system. And remember, we abbreviate thermal and phase energy as ETH and EPH. So again, LOL charts because they kind of look like LOL, but the real name is energy bar charts, and we're representing energy changes in and out of a system. So in this case, we're talking about water vapor condenses on a cold glass. So when we look at our E thermal, let's remember what our bars mean. We'll make a little key over here for ourselves. You should have this written down on your worksheet, of course, but in case you don't, 1 bar of thermal is cold, 4 bars of thermal is hot, and then your 2 and 3 are in between. Now, your neighbor might put something slightly different than you for thermal. That is okay. There's a little bit of wiggle room in thermal energy based on, what you call a 2 and a 3. So you might call something a 2, someone else might call something a 3. You can both be correct. So E thermal has a little bit of wiggle room. E phase has no wiggle room. So this one you have to be dead on because you can't have in between phases of matter. So it's either a solid, a liquid, or a gas. It's not going to be both. So we've got solid is going to be our 1, liquid is going to be our 2, and then if you remember, nothing is 3. You are never going to use 3 bars of E thermal. You don't use it. It doesn't exist. 4 is a gas. And that's because there's such a big difference between a liquid and a gas. Liquid particles are still pretty close together, not as close together as solid particles, but pretty comparable, just a little more disordered. Whereas gas particles are just a huge difference. I mean, a gas is 1,000 times less dense than a liquid. It's a gigantic difference. So we just totally skip that 3 to show it's a really big energy change between a liquid and a gas. Okay, so in this case, we're looking at water vapor condenses on cold glass. So if it's water vapor, this question doesn't give us a ton of information. So it might be like 4 bars really hot water vapor. It might be 3 bars more like room temperature. I'm just going to give it 3 bars. Again, 3 or 4 is fine here just because we don't have the information. We don't know if it's like steam from a pot of boiling water or if it's just some water vapor that happens to be in the air at room temperature. So we'll just go 3. Now we do know because it's vapor, that's a gas, that we have to have 4 bars of E phase. That is non-negotiable. So 4 bars of E phase is non-negotiable. That has to be it. It says water vapor condenses on a cold glass. So we know it's going to end up cold. So again, 1 or 2 bars there. It's condensing, not freezing. So I'm probably going to give it 2. Like it's cold, but it's not frozen. If you gave it 1, that would be okay. I'm going to give it 2. And again, non-negotiable though, condensing, remember that means gas to liquid. So it's ending as a liquid. That's 2 bars as well. So 2 bars for E phase, non-negotiable. E thermal, a little bit of wiggle room there. No wiggle room in E phase. And I forgot to put our system in here. Remember in your circle, just goes your system, what you're measuring. So in this case, we're observing the water. So I put water in the middle. That's my system. Okay, so this is great, except right now it currently doesn't follow the law of conservation of energy because we have a whole bunch of energy over here and less energy over here. And energy doesn't just disappear. It can change forms. It can move in and out of a system, but it doesn't just disappear. So we have to figure out where that energy went. So I like to count up my total bars. I've got 1, 2, 3, 4, 5, 6, 7 bars over here. And then I've got 1, 2, 3, 4 bars over here. So the difference is 3. I go from 7 to 4, so I lose 3 bars. So 3 bars, 1, 2, 3, and then I draw an arrow to show they are leaving the system. So that arrow is going out, away from the system. It's pointing away from the system. If it was pointing in towards the system, that would mean energy in. If it's pointing out, away from the system, so energy goes out. I have 3 bars that are leaving the system because I went from 7 bars to 4 bars. So 3 bars leave. When energy leaves the system, we call that exothermic. So this transformation of water vapor condensing on a cold surface is exothermic. Energy exits the system, or heat, thermic heat exits the system. And so that is our LOL chart. So your keys are to make sure that your E phase is correct. There's no wiggle room there. And then at the end, make sure you account for all your bars. You can't just have bars appear or disappear. You need to account for all of those energy bars. And that's your energy bar charts.